Welcome back to the AI Frontier podcast. Today, we're diving deep into the world of autonomous driving, and we have a truly groundbreaking paper to discuss. Joining me is lead researcher Name, a leading researcher in the field and the lead author of this paper, titled Planning Oriented Autonomous Driving. Also with us is field expert Name, a renowned expert in autonomous vehicle development. Thank you for joining us. It's a pleasure to be here.
Thank you for having me. I'm excited to talk about our research.
So, let's start with the big picture. Autonomous driving is a complex challenge, and there's been a lot of progress in recent years. What makes this paper so unique? Why the focus on planning-oriented design?
That's a great question. Traditional autonomous driving systems typically break down the problem into separate modules: perception, prediction, and planning. Each module is often treated independently, which can lead to cascading errors and difficulties in coordinating information across the system. We argue that this modular approach is not optimal for achieving truly advanced and reliable autonomous driving. Instead, we propose a planning-oriented framework called UniAD. UniAD emphasizes the ultimate goal of the system, which is planning, and ensures that all preceding tasks, perception and prediction, are designed to contribute to that goal.
That's really fascinating. How does this approach compare to the prevailing trends in autonomous driving research? Well, Leadres is hitting on a critical point. The autonomous driving field has been increasingly moving towards end-to-end systems, where all the components are learned together. However, many of these end-to-end systems still lack a strong focus on planning, which is crucial for safety and efficiency. UniAD's approach of prioritizing planning and designing all other tasks around it is a significant step forward. It could lead to more robust and reliable autonomous driving systems. So, can you break down the UniAD framework for us? What are the key modules involved?
UniAD is comprised of 5 core modules. Let's start with perception. We have 2 modules here: TrackFormer and MapFormer. TrackFormer is responsible for detecting and tracking objects in the environment, and MapFormer performs online mapping, segmenting road elements like lanes, dividers, and pedestrian crossings. These modules provide essential information for understanding the driving scene.
So you're essentially creating a dynamic map of the environment in real time without relying on pre-built HD maps?
Exactly. And this is where the planning-oriented design comes into play. We're not just trying to achieve accurate perception for its own sake. We're designing these modules to provide the information necessary for the downstream planning module. Then, we have our prediction modules. First is MotionFormer, which forecasts future trajectories of all agents in the scene, including the ego vehicle. This is crucial for anticipating how the scene will evolve and planning safe maneuvers. And finally, we have OCFormer, which predicts multi-step future occupancy. This helps us avoid collisions by determining which areas will be occupied in the future.
This is all very interesting, but I have a question. How do you ensure that all these modules are effectively communicating and working together? How do you handle the information flow from one module to the next?
That's a great point. We use a novel query-based design to connect all the modules. Think of queries as specific questions that each module poses to the BV feature, which is a representation of the environment in bird's eye view. For example, TrackFormer might ask, what are the positions and trajectories of agents in this area? Or MapFormer might ask, what are the lanes and dividers present? This query-based approach allows for flexible communication between modules and enables them to share knowledge effectively.
This sounds like a more natural way to represent information compared to traditional bounding boxes, which can be rigid and prone to errors.
Absolutely. Queries are more expressive and allow us to model complex relationships between agents and the environment. Now let's talk about the final module, the planner. The planner receives information from all the preceding modules, including the ego vehicle's predicted trajectory and future occupancy. It then generates a safe and optimal plan for the ego vehicle, ensuring that it avoids collisions and reaches its goal.
So, you're essentially training a neural network that learns to drive in a more holistic way, considering all aspects of the driving scene simultaneously.
Precisely. And the key is that we train all these modules jointly, allowing them to learn to cooperate and optimize for the ultimate goal of safe and efficient planning. This is a departure from the traditional modular approach where each module is trained independently.
Let's delve into the results now. What did you find about the effectiveness of this planning-oriented design?
We conducted extensive experiments on the challenging New Scenes dataset, which is a multimodal dataset for autonomous driving. Our results showed that UniAD significantly outperforms existing state-of-the-art methods in various aspects, including motion forecasting, occupancy prediction, and planning. We found that the joint optimization of all modules leads to a significant reduction in prediction errors and collision rates. In particular, the inclusion of both motion forecasting and occupancy prediction modules is crucial for achieving safe and efficient planning. We also demonstrated that incorporating both tracking and mapping modules greatly improves motion forecasting performance.
Can you elaborate on some of the key findings from your experiments?
Sure, we found that UniAid achieved a 38.3% reduction in minimum average displacement error, min-ADE, compared to PNP-net, a state-of-the-art vision-based end-to-end method for motion forecasting. We also saw a significant improvement in occupancy prediction, with a 4.0% increase in IOU near compared to Fiery, a leading method in this domain. And in terms of planning, UniAD reduced both L2 error and collision rate by over 50% compared to STP3, a top-performing planning system. These results clearly demonstrate the advantages of our planning-oriented design.
These are impressive results. What are your thoughts on these findings? How do they fit into the larger landscape of autonomous driving research? I'm quite impressed. These results demonstrate the value of a holistic approach to autonomous driving. The performance gains in all aspects, from perception to planning, are significant and indicate that UniAD is a powerful system. Furthermore, the paper's focus on online mapping is particularly relevant, as it reduces reliance on expensive and potentially outdated HD maps. This is a key step towards developing autonomous vehicles that can operate in diverse and dynamic environments. However, every research project has its limitations. Can you discuss some of the challenges and areas for future research?
Yes, absolutely. One limitation of our current framework is its computational complexity. Coordinating a comprehensive system with multiple tasks requires significant computational power, especially when trained with temporal history. We need to explore ways to optimize the system for lightweight deployment, perhaps by developing more efficient architectures or using model compression techniques. Another challenge is handling long-tail scenarios, which are rare events that can be difficult to predict. For example, our system might struggle with situations involving large trucks or trailers, or in very dark environments. We need to further investigate these scenarios and develop strategies for improving the robustness of our model. Finally, we plan to explore incorporating more tasks into UniAD, such as depth estimation and behavior prediction, to further enhance its capabilities.
Those are important points. What are your thoughts on these limitations and how they might be addressed? I think these are valid concerns. Addressing the computational complexity is crucial for real-world deployment, and research into more efficient architectures is indeed essential. Long-tail scenarios are a persistent challenge in autonomous driving, and the authors are right to highlight them. One potential approach could be to incorporate data augmentation techniques to generate more diverse training data that includes these rare events. And finally, I agree that exploring additional tasks is a promising avenue for future research. Adding tasks like depth estimation and behavior prediction could significantly enhance the system's understanding of the driving scene and improve its overall performance. This has been a truly insightful discussion. To conclude, what is the broader impact you hope this research will have on the field of autonomous driving?
Our goal is to push the boundaries of autonomous driving by demonstrating the importance of a planning-oriented approach. We believe that this framework, UniAD, has the potential to lead to safer, more efficient, and more intelligent autonomous vehicles. By focusing on the ultimate goal of planning and ensuring that all other tasks contribute to it, we can create systems that are better equipped to handle complex and dynamic driving scenarios. We hope that our research will inspire further exploration of planning-oriented design and contribute to the development of reliable and robust autonomous driving systems that can benefit society.
This has been a fascinating discussion. Thank you both for your insights and for shedding light on this important research. Do you have any final thoughts? I think Epkanet and his team have made a significant contribution to the field. UniAD is a promising framework that shows the power of integrating different tasks for improved autonomous driving performance. We're on the cusp of a revolution in transportation, and research like this is crucial for making autonomous vehicles a reality. Thank you both for your time. Thank you both for joining us today. Listeners, I hope this deep dive into planning-oriented autonomous driving has given you a better understanding of the challenges and opportunities in this exciting field. We'll continue to explore the latest advancements in autonomous driving and artificial intelligence right here on the AI Frontier podcast. Until next time, stay curious.